we're able to move more quickly, that the development and operations processes that we follow for working with our data integration tooling needs to become more agile and faster to embrace change as well. So we really strongly believe that the ways of doing data integration in the past, over the last 30 years or so, are no longer sufficient to meet the future. There's been a lot written about this in the past few years. We have discussions coming from analysts such as Forrester about the enterprise data fabric. We see data fabrics also being talked about from a Gartner standpoint. We see data mesh in the news a little bit. The ThoughtWorks folks from Microservices fame have kind of been talking a lot about data mesh. We see stream processing as being brought into the data integration category as, you know, really a new paradigm for doing data management. And interestingly, we also see the emergence of service mesh capabilities, really the set of technologies around microservices, Docker containers, and Kubernetes type mesh deployments for applications, as really kind of driving a lot of change in the software industry. So what we're thinking about here is that really the future of data integration, where data integration evolves to in the future, is away from these hub and spoke type architectures and more towards a mesh type capability, where a mesh is about leaving behind the characteristics of monolithic data integration capabilities and moving more towards a modern multi-cloud, you know, data-driven platform for supporting enterprise applications, enterprise analytics, and the data services that drive our business units' data products. So this presentation will talk through a lot about that. The evolution that's been going on over the last 30 years has been happening progressively. It's been coming in waves. And what we've seen historically around data management architecture over on the left-hand side of this chart is that the hub and spoke architectures of the past, kind of the Kimball and Inman type of architectures, have served us very well for around 3 decades, but they're aging at this point. We've seen these approaches for integrating OLTP databases via batch ETL jobs into operational data stores, and then feeding dimensional data warehouses, data marts that are optimized for different kinds of reporting and analytics and data mining use cases. Lots of ETL and batch processing, lots of relational centric technologies. As we saw the emergence of the big data technology stack in 2010, we began to hear about what's called the Lambda big data architecture, where batch processing and stream processing operate side by side. With big data, we have a more flexible set of tools that work more effectively with unstructured and semi-structured data. And we've really seen the importance of what we call a scale-out architecture rather than a scale-up architecture. So we've definitely moved the needle here with the big data technology stack, but it's still fundamentally a monolithic type of architecture. The Lambda architecture, and even the more modern version, which we call the Kappa architecture, which focuses more on streaming, still predominantly require a host of technologies and frameworks that all come together in kind of a monolithic type of architecture. It's an all or nothing type approach towards building these data lakes. And often the centricity of the data, whether that's a data lake in the cloud or a data lake on Hadoop, requires that the central idea by definition is that you're bringing the data into a common storage area. In contrast, this idea of a data mesh is one where the processing and the storage and the events related to the data can all be distributed throughout a different set of infrastructure. It's designed to kind of more easily embrace the type of environments where we see Internet of Things data sources. We are able to process and activate data routines that work at the edge of the networks rather than having to bring them to the central public cloud processing storage areas. So it's much more of a distributed concept where the data, the logs, and the streaming pipelines can all flow seamlessly between different sets of infrastructure. So we've been talking about this for a while here at Oracle for most of this year so far, and today's presentation is really looking at about part 4 of a 4-part series. In part 1, we looked at the alignment between change data capture tools and distributed commit logs. Part 2 We looked at the alignment between microservices, application architectures, and change data capture replication. And then part 3, we really pulled together an end-to-end demo to kind of show what this looks like with a variety of different data topics. So today, we'll drill into how all of this comes together towards the future of data integration architecture and data integration tools. So first, let's take a quick look at where integration tools have come from. Historically speaking, going back to the 1980s, we've seen really 3 classes of integration patterns at the core, at the heart of what our vendor-provided tools. There's kind of process-oriented layer that focuses a lot on application integration, integrating applications at the API layer, tying together long-running business processes that move between multiple applications. And this is, very well suited for our customers and all of us that may have multiple applications acquired over the years through acquisition or through growth. And we need to apply business processes that span multiple applications. And so these types of business process-oriented or application-oriented models are very well suited for that. The data integration tools, in contrast, have really been focused quite a lot in what we call the data tier. The data tier tools have been, doing bulk processing with ETL, data replication with change data capture, data federation, data virtualization. And really, the central characteristic of a data integration tool, in many ways, has been to provide very strong data consistency. And so for our customers that have very high value data, financial data, economic data, data about retail transactions or about customers or medical, anything that's can be highly regulated or highly valued, it's extremely important to handle this data in with what we call strong consistency. Strong consistency means that the data can be trusted for the regulatory use cases, but also has extremely high levels of durability and survival in case of disasters or outages. And so traditional data integration tools like change data capture, replication, ETL tools, data federation tools, streaming integration tools have all to one degree or another really maintained what we call these ACID level transaction guarantees and provide high durability scenarios. And these data consistency guarantees, for example, are extraordinarily difficult to solve at the business process layer, whereas at the data integration layer, it's just really part of the core use case for what the tools provide. Similarly, for very high volume use cases where there's lots of data moving either in batch or in real-time processing, we're talking about potentially terabytes per hour at the data tier. The data integration tools tend to be much more optimized for low-level data movement. This could include block-level movement, and even when we're talking about logical data movement, they tend to be in the binary formats of the data stores, as opposed to business process tools or application integration tools, messaging tools. Generally, those kinds of tools are working with data that is in more of a payload format or a document format, which generally requires much more semantic conversion to get the data to those tiers. The data integration tools, in contrast, generally work at a more native level with the raw storage formats of the data. And then third, the purpose for data integration tools in many ways is to drive use case adoption through SQL clients or SQL clients. And so when you're working with data that has been kind of born in a database or is SQL native, you can transmit and replicate and copy data around in these result set formats that make it much easier for SQL clients to consume. So these have really been the drivers for the different styles of data integration over the years. But meanwhile, what's been happening in the software industry, while data integration tools have been progressing, the rest of the application development world has been gradually adopting design patterns that shift away from what we call monolithic architectures. So these classic monoliths typically have tied together the software layers with the database layers, with the infrastructure layers, and have lots of tight coupling between the different tiers of the architecture. Progressively, as we move forward into what we may call the monolith era or the client-server era, we've decomposed the software tiers, and in some cases, we've been able to loosely couple from the infrastructure and the storage tiers. But by and large, there's still coupling at the logical level between shared databases and in many cases shared frameworks. And these create dependencies that can become problematic from a development and operation standpoint or a DevOps standpoint for continuous integration, continuous delivery. So in the application development world, we've been gradually shifting to the types of architectures we see over on the right-hand side, which are around microservices and mesh type patterns. And so here we're providing software components that are more fine-grained. They're designed to work on a more decoupled type of architecture where the data models or the event models are fully encapsulated in the individual components. And each component is really designed to work as a standalone execution framework. This is really the central characteristic of a microservice. What we have seen recently as well is this concept has been extended to include service mesh capabilities as well, where we're now taking microservices and we're organizing them into clusters or pods that can be managed through software containers and through distributed automation coming from technologies like Kubernetes and OpenShift. And this is generally applying what we call the sidecar pattern for distributed administration of decentralized software components. And so this shift, if you will, from an architecture standpoint, is driving a pretty significant change in what we think of as modern software architecture. So what we're proposing here essentially is that the data integration technologies need to evolve as well to adopt these modern approaches towards software architecture. And so when we look at kind of the classical data integration tools that are out there that really were pure monoliths, these are tools like Ab Initio for ETL, some of the older versions of Informatica Power Center, even in the big data open source space, using technologies like Hadoop or Hive, the Hortonworks data platform, very much classical monoliths. The storage is tied to the compute layers. You can't scale them independently. In many cases, there's fixed hardware requirements in terms of how you need to deploy these architectures. As we've moved more towards the client server and monolith tier in the middle, we've still fundamentally been fixed in a monolithic type of architecture, but there's been some attempt at decoupling the storage from the compute tiers, for example. So now we can run on more open infrastructure frameworks. A lot of these technologies can be provided as what we call a lift and shift to the cloud with a decoupled storage architecture. So these are technologies like the newer versions of Power Center for ETL, technology from Talend, even Oracle's own Oracle Data Integrator, et cetera. But these are still not quite mesh capabilities because of the way the software interdependencies work and the way that the frameworks are spanning across multiple shared components. So in a more classical data mesh type deployment, what you'll see generally is that the technologies can be distributed across multiple virtual cloud networks, that you can distribute the individual functions of a data integration pipeline more seamlessly between customer managed and vendor managed clouds. And so the idea is that you should be able to take an end-to-end data integration solution and distribute that across different runtimes and different infrastructure while still maintaining a span of control around the pipeline execution framework. And so this can be in customer managed environments where they operate their own containers like Docker, container management frameworks like Kubernetes or OpenShift. But these components could also be in public cloud frameworks where they execute in a serverless environment running on third tier cloud vendors such as Oracle or Amazon or Azure. And so these are all what we would consider to be kind of options in the data mesh. And this is actually quite a bit different than what some vendors may have you to believe is a modern architecture, where they're simply taking their legacy data hubs and then running them from the cloud. And so, you know, basically, even if you take a monolith from an on-premise environment and put it in the cloud, you've still got a monolith to deal with there. So you can't evolve these architectures without a fundamental refactoring in how they run. And so, you know, I think many here probably know this already, but you just can't put a set of REST APIs in front of a monolithic architecture and then, you know, call it a mesh or a microservice. It doesn't work that way. And that's because the benefits that we're trying to achieve from these mesh type architectures are to drive down the cost of operations through improving what we call continuous integration, continuous delivery. We need to decrease the errors related to complex lifecycle management for data integration software, and that is by providing a more, you know, decoupled way of integrating data pipeline components so that you can upgrade and migrate and fix issues in smaller, more fine-grained chunks without having to do boil the ocean type upgrades. And then it's really about also improving the pace of innovation that our customers are looking to achieve from their data-driven architecture. You know, it goes back to first principles here in some ways. If data is really the driver for innovation, whether that's through data science or analytics or data services, then we need to do a better job at managing the data in the infrastructure. And the type of flexibility that a data mesh brings is really centered around shifting towards what we call event time. And so rather than working on scheduler time or batch processing time, we're able to provide value to the business units by giving them insights and data visibility from the moment data is born, from the moment that the events happen with the data and the infrastructure. So this additional kind of decoupling and the physical properties of tying into a microservices architecture give you the operational benefits that our customers are looking for: faster lifecycle management, more agile development processes around IT operations, but then from a data standpoint, being able to provide services that are more flexible in real time. And that's really where we get to this idea of a data mesh. It really is about the business ownership. And so the first point that we make here on a data mesh definition is that it's data product oriented. So this idea of data products actually stems originally from the data science domain for individuals that are functional domain experts that maintain and develop the models, the features on the models, and the algorithms or the semantics of the algorithms for the models. What we're using the term here in the context of a data mesh is a more generalized definition of data products, where a data product could be an analytics dashboard, it could be an API that is attached to a data service. A data product could be a document that's output from a set of services. Data products are the collections of data that drive value for our customers, that drive value for our businesses. And when we look at the data mesh from an infrastructure perspective, it's about how do we more effectively help our customers create and manage the data products that drive value. And so that decentralized processing model shifts us away from a classic monolithic approach and towards something that makes more sense in a world where cloud infrastructure, and more importantly, multiple clouds, are part of the day-to-day operations of IT organization. And so this notion of an event-centric, streaming-centric, decentralized processing model for producing data products is really what we're kind of driving towards with this data mesh idea. And so data products in many ways are just projections or views on business objects or data objects that exist in the enterprise. Now, the fundamental problem or challenge from an IT perspective is that data is inherently messy when it's in its raw state. So you need to have this type of logical or conceptual architecture that can apply to how we take raw data events, whether that's from an application tier or a database tier or from a device or an endpoint on the edge of the networks, how we can take those raw events and progressively move them up from a semantic quality standpoint or a meaning quality standpoint, so that eventually they make sense for the business users, for the data product owners that are actually tasked with producing value from the data that's being produced from these applications or devices. And so this is what this type of three-tier conceptual architecture is that we basically look at the world of data as events. All data is born as an event. And so if we can capture those data events from the source, we can then move them through streaming processors to enrich or curate the data, if you will, into what's called a prepared state. And a prepared state is really about having a more trusted level view of the data while the data is still somewhat in a technical format. It may make sense for engineers, but maybe not for business users. And then as we move the data up to the next tier, what we call canonical data, this is where we're now aggregating and joining data into views that will make sense to the business users. And these are collections of data that are aligned to the business's needs rather than to the raw formats of the data that may exist on disk. And so this pathway, if you will, it's almost like a neural pathway, is to take these events that are being continuously emitted from applications, databases and devices, and then provide very low latency way of enriching and joining data so that it's available to these different data consumers. The way that we do that is through a multi-tiered processing model. These pipelines, if you will, can run from any different location, but the idea is to have pipelines that are optimized for different consumers. If you look over on the right, some data consumers prefer to see or need to see the data in an SQL relational format. Other consumers really need to see the data in their rawest event level format. So think data science. I've never heard a data scientist ask for less data. They always want more data, and they want it in its more raw state because that produces higher quality results from a data science algorithm. But as you move up the stack of users, you get into analytics and data mart users. Maybe they're more comfortable working with dimensional or snowflake type models, data vault type models. But then eventually you hit to an application user or a business consumer, and they're mostly comfortable working with business objects. And they're really not even conversant at an SQL level. They need to see data objects in formats that make sense to them from an application user standpoint. And so we can move data through these pipelines in near real time, but there are some trade-offs that happen. If you're interested in mainly the lowest possible latency, the highest possible speed, and the greatest level of fidelity of the data, then you have to accept the trade-off that there's less curation work that's going to be going on. So to get to that highest speed, you're going to decrease the amount of workload and the amount of involvement that's been put on the data at that point, so that you're consuming directly from the raw layer. If you'd like trusted views where you're filtering out bad data, you're enriching missing columns, maybe you're standardizing or normalizing some of the data values that are attached to a column, but you're really now you're massaging or you're enriching the raw events in order to have it make sense for you in your tables. This would be what we'd call a prepared data zone. And then ultimately, to enrich the data to a point where you've now combined it or joined it or aggregated into some type of master data, that is an additional stream. And that is the simplest possible way to consume the data, but you may add some more seconds to the workload for processing. So the central feature of a data mesh is that we should be able to perform all of these actions and steps in a distributed way on multiple clouds and multiple infrastructure, that there should not be any centralized hub type architecture required to do the processing. And that feature, the distributed notion, is one of the hardest things to achieve, but it's really crucial if we want to move away from these monolithic architectures of the past and work within a more modern multi-cloud architecture where most of our large customers, have workloads that are running in a lot of different infrastructure. And so this gives us greater flexibility as well as greater speed when we do lifecycle management for continuous integration, continuous delivery. So being able to, again, process on the edge, process from public clouds, and process nearer to the application, all part of these centralized frameworks. So the key attributes that we look for then in a data mesh are that the physical deployments should be deployable in most infrastructure, different public clouds, private clouds, on-premise infrastructure. You can also run mesh node components in serverless environments for proprietary public clouds as well. So you should be able to deploy these workload patterns in a variety of physical deployment options, either that our customers are managing as microservices and service mesh, or within serverless environments that execute within public cloud infrastructure. The mesh controller should have maintain observability, security, and routing across the node components. And so as you distribute the data, as you distribute the pipelines and the workloads, it's only a mesh if it hangs together. If you've now kind of decoupled everything and so to such a degree that it's not even administratable through a centralized framework, then the only integration you have is really through a Visio diagram or a PowerPoint picture. A mesh controller should give you some level of observability, security, and routing, and that would typically be done either through a common process controller or through a sidecar type pattern where you can observe processing that's happening outside of a direct span of control. What we see for the data mesh as well is that the central feature of a mesh is that it is focused first on streaming pipelines. And so we really, from a philosophical standpoint, a data mesh use case sees batch processing as a special case of stream processing, not the inverse. So historically, it's actually been the opposite. People have started with a batch processing model, and then they've only graduated to stream processing when the business demands it. The processing model for a data mesh actually begins the other way. You start with the assumption that all of your workloads can be event-driven by default, and that the processing workloads can be executed through streaming pipelines. And then you only check down or go backwards to a large batch processing model when you absolutely need to. There's going to be certain corner cases where you just hit the laws of physics around, some batch processing approach, or even legacy systems that may not have the openness required to drive an event-driven model. For those special cases where you need to revert to a batch processing approach, the eventing system should be able to drive it through the observability and routing of a mesh controller framework. So even if the data needs to move through alternate protocols, we should be able to observe and handle routing through the mesh, even for those batch processing models. It's important now, modern applications all use what we call polyglot data. Polyglot data is a fancy word for just saying that data can have different shapes and different data models attached to it depending on your use cases. But what we see, in the real world here is that, more and more applications are making use of NoSQL engines for JSON type processing, or there's columnar data formats for optimized analytics. There's graph data models that are used for certain types of application use cases. And a mesh framework, a data mesh framework, needs to be successful in handling both the highly structured end of the spectrum for data semantics, as well as the semi-structured end. And so this means that in the frameworks for moving the data, for routing the data, for transforming the data, you must have the core central kind of data integration properties of being able to maintain strong consistency, preserving ACID transactions, so that if you're moving, let's say, financial data through the data mesh, that you can trust that all the transactions are there, that you're not missing transactions that need to be there for an accounting and regulatory purpose. So that ACID level strong consistency needs to be there. Likewise, the mesh framework needs to be flexible enough to handle a lot of these kind of modern payloads that are attached to microservices applications, such as JSON and Avro and graph-based payloads as well. So those need to be able to flow seamlessly through the mesh. We also expect a high level of data governance. Data governance here would include cataloging capabilities, data lineage or provenance capabilities, as well as data validation, in order to provide guarantees that the expected records have moved from one node in the mesh to another node in the mesh. And then ultimately, one of the largest benefits we expect from a data mesh framework is that we simplify the development and operations lifecycle controls, that we're able to move more quickly and have more successful migrations and upgrade processes. And so we'll have some situations where customers manage their own infrastructure using containers and service mesh frameworks. And we'll have other situations where customers rely on public cloud vendors to manage the infrastructure and provide serverless execution engines for some of these node endpoints. And a mesh should be able to deploy workloads in a customer managed environment, as well as a cloud vendor managed environment for serverless execution. So these are some of the key kind of technical characteristics that we look for in a mesh type framework. And to give a couple of examples here, the first of which is to look at some things that we can do with Oracle GoldenGate. We do look to deploy a data mesh as a mesh of microservices that can run on multiple infrastructure endpoints, route data from devices and things on the edge of the networks through the gateways into public cloud frameworks that might not be Oracle's cloud. They could be other public clouds, working with applications as well as cloud customer infrastructure, and ultimately driving data pipelines into analytic environments that could be, again, Oracle for technologies like Oracle Autonomous Data Warehouse, but also into other cloud vendor analytic environments such as Azure Data Lake Gen 2 as well. And so being able to support this type of distributed framework or distributed architecture for routing data, moving data, providing transformation workloads, applying different types of business rules and policies, stream processing and stream analytics capabilities as part of this mesh is something that we see as a successful implementation or instantiation of a mesh framework. As I mentioned previously, another example that's worth pointing out is maintaining consistency in the data pipelines is really crucial, particularly as a lot of the so-called modern frameworks for doing messaging don't actually maintain transactional consistency themselves. So here I'll just use Apache Kafka as an example. I shouldn't have to say this, but it's worth reminding people, Kafka is not a database. Kafka does not provide ACID level transaction guarantees for strong consistency. And so what happens is when we have customers that attempt to use replication tools such as GoldenGate to move messages into Apache Kafka, GoldenGate is providing the additional semantic enrichment in order to maintain transaction consistency that then the consumer of the messages has to be responsible for. And so in this case, GoldenGate is carrying information such as system change numbers and commit sequence numbers. We decorate that metadata into messages that get put into the Kafka partitions, as well as we also decorate transaction ops types as well, so inserts, updates, deletes. And then what happens is on the consumer side, There's established patterns that the consumer can use to maintain transaction boundaries between, say, item header and item detail type information, so that you're not reading inconsistent data off of the Kafka topic. So, having these patterns and technologies and approaches to maintain data consistency in a mesh type framework is really crucial to be successful if you're moving high value data. So the third example that I'll provide here is around doing the stream processing. And this is really fundamentally about shifting our customers from a batch processing model that in the past could take 24 hours to several days of processing based on dependencies between different tiers, and dropping them down to latencies that can be measured in terms of single-digit seconds. And so these stream processing pipelines that are used for ETL processing now can capture events as the events are born from the applications, from the databases, from the devices, and then move them through these ETL pipelines in real time. We can do lookups to static tables. We can provide what we call tumbling or sliding windows to perform aggregations on groups of events that come in together. You can stage the data in these pipelines so that they're applied in micro batches to different output technologies such as data marts and data warehouses or data science lakes. And importantly, you can also run analysis on the data while it's moving through the processors themselves. So if you need to do time series analysis, if you want to do data classification, or even apply machine learning scoring models in line to the stream processing, you can do all of that while the data is flowing within a specified time window in the stream processing framework. So this is really fundamentally how we move away from classical batch ETL processing and towards the future, which is continuous transformation and loading. And so it's these kinds of technologies that will really take us out of the era of monolithic data architectures and into the era of a distributed data mesh. So tactical opportunities, we've touched on a number of these already through the presentation, loading data lakes, shifting batch processing ETL jobs to continuous processing CTL jobs, doing replication across regional virtual cloud networks, applying data ops for microservices so you improve the reliability of data in an operational environment as well as an analytic environment. These are the kinds of things that IT organizations can achieve by adopting a data mesh. But importantly, when we look at what can the business achieve, it's about empowering these new use cases that drive digital transformation or business transformation. And so, so many of our customers are looking to move to a next best action model for driving real-time offers or real-time marketing. It's these eventing frameworks that allow us to shift to what we call a system of engagement, where we're engaging our customers in real time, in real world time, rather than in batch processing and asynchronously via emails and other kind of asynchronous models. It's these event-based mesh type architectures that allow us to get to a real-time framework. Same thing with logistics and location intelligence. What I always tell people is, from an integration standpoint, the highest value insights that you get from data are when you combine events that are coming from the real world with events that are happening in your enterprise applications. And so that intersection of understanding what's happening in the real world alongside the same moment that you're receiving events in your business applications, those are when incredible insights can be used to drive business value. So same thing with supply chain and predictive maintenance type use cases. Any of our larger customers that manage real world items in the real world, or that need to perform maintenance on physical devices that can deteriorate over time, we can now monitor and manage those kinds of devices in real time. And again, importantly, combining those physical world events with what's happening in the enterprise software world is where you really start to drive these monetizable data services that really qualify as what we call genuine business transformation opportunities. So let's wrap up by just taking a quick look at what we're doing on the GoldenGate side to fulfill these data mesh use cases. You know, the thing that we're bringing as Oracle, particularly with Oracle GoldenGate, is that, you know, we're really focused on these trusted data use cases. There's, you know, around 8,000 customers, 8,000 really of the largest businesses in the world already depend on technologies like GoldenGate for high availability and disaster recovery of mission critical databases. And not only Oracle databases, by the way, mainframes and tandem nonstops, payments engines, et cetera. And so these high-speed data replication use cases that we provide for what we call real-time event detection on the data stores is really a unique capability that only GoldenGate is fulfilling in the market right now. That intersection of real-time events on trusted data. GoldenGate is really that trusted data engine that is trusted to never lose data in even the most kind of intense situations of regional and local outages of data centers and hardware and software. This is a transaction-safe framework, so we are trusted with the most important kinds of financial and economic and retail data in some of our largest customers globally. And again, a lot of the other types of integration tools, you know, can't really say that from a transaction standpoint or recoverability standpoint. And then finally, we've added now the event stream processing that works at web scale, so processing billions of events per second. And we can bring those kinds of scale out capabilities to the stream processing environment. So these are kind of the special areas that we're bringing as Oracle. You know, other vendors may bring other benefits, but these are the benefits, the unique differentiators that we're bringing as Oracle. So, you know, it's important to understand that GoldenGate itself is a microservice, or is really, it's a collection of microservices. So for those of you that know GoldenGate already, the newest version of the GoldenGate architecture that's been out for really the last 3 or 4 years at this point is called GoldenGate Microservices Architecture. This is the future of the GoldenGate platform. It's what we run on the cloud, and it's also the primary software strategy for the GoldenGate software going forward. And so we have a collection of 5 microservices. Everything is fully REST native. We fully encapsulate our data repositories, and we provide 100% of the native GoldenGate replication capabilities through these microservices. So everything's addressable over cloud-based protocols. REST, you don't have to run, you know, kind of super user privileges at all, or you don't have to run a command line at all if you don't want to when managing GoldenGate any longer. So GoldenGate itself continues to add more sources and targets to support event capture on the left and event delivery on the right. And the kinds of use cases that we see for hypergrowth in the GoldenGate ecosystem really are around in the microservices space, what we call transaction outbox capabilities, where we're providing event-based replication, data event-based replication from a variety of different sources to destinations all across the enterprise. These could be big data lakes, they could be cloud analytics, cloud data warehouses, cloud data lakes, could be NoSQL engines, could be stream processing environments. And then of course we continue to provide our customers with a lot of capabilities to go database to database. But GoldenGate's also been adding non-database capture technologies as well. So we can capture from technologies like Cassandra, JMS, Apache Kafka, as well as a number of SaaS-based cloud applications as well. So this really becomes kind of that event-based transaction outbox for the entire enterprise. What we're really moving towards from a directional standpoint is to provide a single pane of glass for the real-time data mesh. And so the first step of which we just described, which is the event detection and the event replication using the core GoldenGate framework. And what we're adding now, and what we have added, is all of the real-time stream processing capabilities to do the inline processing within an in-memory scale-out framework running on open source technologies. And so this allows us to do millisecond level processing of ordered events on an in-memory stream. And so we can take any of the input from GoldenGate, but also directly from Apache Kafka or JMS, provide stream analytics, provide continuous transformation and loading. Of course, the framework includes the change data capture as well as the data replication. We have governance capabilities baked into this framework around data catalog, data verification, a variety of different encryption and security controls, including role-based security. And from a mesh standpoint, it's important to know that these deployments can run anywhere you like. And so they can run on bare metal, they can run in Docker containers, they can be managed through Kubernetes or OpenShift, they can run on Oracle Cloud, they can run on AWS Cloud, they can run on Azure Cloud, and you can execute any of these operations from those multi-cloud environments, thereby kind of giving you that physical mesh of distributed services. So again, the stream processing framework, we're able to ingest events directly from the GoldenGate change data capture and replication framework, but we can also ingest events that have been produced by any Kafka producer, as well as JMS, and then we have native integrations with the Oracle Cloud streaming frameworks as well. So there's a variety of ways to bring events in. It doesn't have to just be change data capture or just be database replication. These events can be coming from applications, they could be logging events, they could be device level IoT events. And then once you get the data into the pipeline, you can merge these event streams and aggregate the data and then fire alerts or do analytics off of the combined data streams, some streams coming from databases, some streams coming from applications, some streams coming from devices, and then produce insights directly off of those pipelines. So the kinds of things, it's a low code environment tool that you develop these pipelines from a graphical standpoint. You can do time series analytics. You can do geospatial analysis. It ships natively with a Google Maps framework that you can plot coordinates on a map and then look for events that are happening within the mapping framework. We also allow our customers to bring in custom mapping tiles so that they can look for geofenced based events within custom maps that they bring. And from a data science standpoint, you can take any data science model that's been produced, and then you can productionize it by moving the production model into a pipeline that's running data in real time. And so that gives you the ability to do online scoring. You can score customer behaviors, recommendation engines. You can look for fraud detection, fraud analysis in the pipelines, et cetera, and those can all be plugged directly into the pipeline. The core technology that we have in the streaming framework, very proven. We've actually had the core technology for over 10 years, and about 3 years ago, we refactored it to run in these open source frameworks like Apache Kafka and Apache Spark Streaming. But the central intellectual property that we have is around what we call a complex event processing engine that happens to run within a Spark context. And so that's really where we tie together the high value IP that Oracle's bringing. We've got this core IP around Oracle GoldenGate that provides the change data capture, the data replication capabilities for supporting very high value trusted data, disaster recovery scenarios. And then we tie that in together with this extremely powerful event processing engine that now can run at web scale on open source technologies. And we can support these use cases like continuous ETL processing, event data pipelines that run continuously, time series analysis, real-time AI and machine learning. And when we take that together, that's really where we see the data mesh capabilities coming together, supporting high-value business use cases in a distributed architecture that's focused on providing customers high-value data products. So, again, that Oracle focus for us is on consistent enterprise data. When you think about what does Oracle do best, we work best with high-value ERP applications like general ledger, HR, supply chain. We work best in the financial industries, logistics, inventory management, operational data availability, and all of these analytics use cases, trusted data lakes, large-scale data warehouses and data marts, providing dependable analytics for our customers. And that's really our angle, if you will, on the data mesh and what we can bring as Oracle that other vendors can't. And so, I'll leave you with a couple of thoughts. Definitely reach out to the Qualogy team or your Oracle team for a demo. We'd be glad to bring in some technologies and tools and help provide a demo of some of the concepts that we've talked about today. Take a look at the Forrester report that ranks Oracle #1 in data fabric strategy across all vendors globally. And you can see more information that we've put out around the data mesh, and in some cases kind of going deeper into these GoldenGate and Kafka topics from YouTube. And then we also have a free trial. If anybody actually wants to just go try any of this with the GoldenGate Stream Analytics, anybody can try that right now. You get some free credits and you can run it. It's a fully baked, encapsulated environment on the Oracle Cloud. You don't need to bring anything. You don't need to bring Kafka or Oracle databases. We've put it all in one container for you, and we've got sample applications and sample data that you can try. So it's all out there for anyone to give a shot. So take any of these next steps, give it a try, and reach out to Qualogy or Oracle for any help that you might need. So with that, I think I'll wrap up, and if there's questions, I'll be glad to take them. Otherwise, we can tie this off.
Okay, thanks, Jeff, for your session. I can't see any questions, so you now have the chance. If there aren't any questions, then we'll wrap it up. And I want to thank you very much for your presentation for today, and everyone. I hope you enjoyed it, and maybe see you the next webinar next week.